welcome to all. I Hanis binti Hilmi from FOAS 120530 and my group members are going to present about high performance liquid chromatography.
Our group consists of 3 members. The first one is Hani Suraya binti Hilmi. The second member is Nur Hamizah Izzati binti Muhammad Moin. The third member is me myself, Nur Amiratika binti Amir Hamzah.
HPLC or high performance liquid chromatography is a chromatograph that uses a liquid mobile phase to separate the components of a mixture. Analytes are first dissolved in a solvent and then forced through the column under high pressure. HPLC is very versatile and can separate many types of mixture including non-volatiles and heat-sensitive compounds, organic, inorganic and biological samples, synthetic or natural polymers, and thermally unstable substances. There are many advantages of HPLC. HPLC has greater sensitivity due to its variety of detectors. It has reusable column for multiple analyses and suitable for ionic species and large molecules. It allows sample collection using fraction collectors. For its application, HPLC can work for any compound that dissolves in a liquid using the mobile phase. It can be used for analysis or preparation of highly pure compounds in small or large amounts. Common uses include analyzing sugars, pesticide residues, organic acids, lipids, amino acids, toxins, and vitamins, and etc. Let's get through to the principles of high-performance liquid chromatography (HPLC). HPLC begins by injecting the solid analytes onto the top of the column. Separations occurs as the analytes and mobile phase are pumped through the column. Each component ellipses from the column as peak on the reorder. The response of detector to each component is displayed and known as a chromatogram.
The objectives of the experiment are to determine the retention time Tr of N-butanol and 2-propanol, second to determine the effect of temperature on Tr and Rs, to identify the component as present in a unknown sample, and lastly is to identify the components present in a standard mixture based on Tr.
Have you ever wondered how scientists identify and separate complex mixtures with precision? HPLC plays a crucial role in industries ranging from pharmaceuticals to food safety. In this presentation, we'll break down the instrument step by step, exploring how each component contributes to its remarkable functionality. High performance liquid chromatography, or HPLC, is a highly efficient assembly line. Each part has a critical role in ensuring the accurate analysis of samples. In the next slide, let me walk you through its main components and functions. Here's a breakdown of each component and its functions. Number 1. The solvent acts as the mobile phase that carries the sample through the system. It helps separate components of the mixture. Number 2. It delivers the mobile phase at high pressure to push it through the system and ensure a steady flow. Number 3. Introduces the sample into the HPLC system in a controlled and precise manner. Number 4. The heart of the HPLC system, where the separation of sample components occurs based on their interaction on the stationary phase inside the column. A function of a detector is that it detects and measures the separated components as they elute from the column, providing data in the form of peaks. 6. It functions as recording and analyzes the detector's output, producing a chromatograph for interpretation. Number 7. It collects used solvents and samples after they pass through the detector to keep the system clean and safe.
As you can see, this is the result of our HPLC experiment, which through the caffeine standard, we got the retention time is 2.482 at the peak area of 6,249.48. This data suggests a sample with dominant compound alongside other substances in varying concentration. Peaks with shorter retention times might represent smaller, more volatile molecules, while later peaks likely correspond to larger, less volatile molecules. Let's compare to the first results and the second results. The first result represents a single peak with the retention time, width, area, and height, with the area percentage being 100%. This indicates a pure sample, likely the caffeine standard, as there is only one peak present, representing 100% of the chromatogram's area. When compared to these both set of results, the second results show that peak 4 closely matches this caffeine standard. Both have similar retention times, 2.481 minutes, and comparable peak characteristics such as high area 7001.12 and significant height. This suggests that peak 4 in the data likely represents caffeine as it aligns closely with the caffeine standard's retention time and intensity profile. The presence of other peaks in this data indicates that the sample is a mixture with caffeine being the dominant component. So let's move on with the ppm calculation of the caffeine. So the stock solution of the caffeine. First, we must find the concentration, which is 10 milligram of caffeine is divided with 10 ml of the volumetric flask to get 1 milligram per ml. So after the dilution, the final volume is 20 ml after the initial 10 ml was added with the dilution of 10 ml. So 10 ml of the initial earlier was divided with 20 ml of the final volume to get 0.5 milligram per ml. Since 1 milligram per ml is equal to 1000 ppm, so 0.5 milligram per ml is equal to 500 ppm. For the working solution of the caffeine, we use the formula of M1V1 equal to M2V2. M1 is 1 ml of the stock solution. V2 is 10 ml of the volumetric flask equal to M2, which is 0.1 mg of solution, with V2 remain unknown. So 10 divided by 0.1 equal to V2, we got 100 ppm for the working solution of the caffeine. So for the concentration of caffeine ppm for unknown solution, we use the formula of response factor of the caffeine from the result earlier equal to peak area of the caffeine standard divided by concentration of the caffeine standard. So RF of the earlier results equal to 6249.48 for the peak area of the caffeine standard and 500 ppm for the total concentration of caffeine standard. So RF is equal to 12.49, which is good since the RF must be more than 9 for a good result. For Coke, the concentration of the caffeine ppm is equal to the peak area caffeine in the sample divided by the RF of the earlier calculation. So ppm equal to 0.07001.12 for the peak area caffeine in the sample divided by 12.49 in the RF earlier to get 560.53, which was rounded into 561 ppm. So
The experiment successfully achieved its primary objective of determining the retention time for N-butanol and 2-propanol. The obtained retention time provides insight into the separation of these compounds based on their physical and chemical properties, particularly their volatility and interaction with the stationary phase. By examining the retention time of the component in the standard mixture, the gas chromatography experiment was able to successfully identify them. The different TR R value were good indicator of the individual compound and show how well GC separate and characterize the components of the mixture based on their volatility and interactions with the stationary phase.